The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm Desiree Schell. This week we're exploring what we know and what we don't know about the brain and its connection to behavior. A little later, we'll get the real scoop on the difference between the left and right hemispheres of the brain, and we'll look at criticism of neuroscience and the difference between reasonable caution and outright hostility. But first, my guest is Robert Burton, MD, neurologist, novelist, and author. A graduate of Yale University and University of California at San Francisco Medical School, he was formerly chief of the Division of Neurology at Mount Zion UCSF Hospital and associate chief of the Department of Neurosciences. He's the author of On Being Certain, Believing You Are Right Even When You're Not, and the new book, A Skeptic's Guide to the Mind, What Neuroscience Can and Cannot Tell Us About Ourselves. Good to have you here, Robert.
My pleasure.
Maybe let's start out with what your perspective is on how neuroscience is currently being presented to the public.
I think maybe it would be easier if what I do is I would start back with 300 years of history in 3 sentences.
Do tell.
Everything that's written in the field of neuroscience or anything that's written in the field of exposition, by definition, presumes that reason will carry the day. In other words, ever since the days of Enlightenment, and I suppose probably all the way back to Aristotle, the assumption is that irrespective of how our brains work, our faculties of reason are capable of overcoming some basic limitations. And I think that's been the sort of backdrop to neurology for me since I've been in it for 40 years. And basically in seeing patients through the years, you see certain types of conditions where people cannot recognize what side of their body they don't see. They think of their wife looks like a hat or something like that, where you realize that there are some basic impediments to how we think about how the brain works. Now, this same brain is the one that's studying itself. So if we wanted to make this very simple, I guess my biggest question is, how can we know how our mind is thinking about the mind if the mind is subject to all the various kinds of irrational biases that we hear about in the news every day? And so my starting point for writing this was really as a sort of visceral reaction to the overwhelming sense of reason that each of us has, despite the fact that anybody who reads any scientific literature now realizes that we have all these various irrational biases. And so that's sort of my starting point.
Okay, that is a lot to unpack. You mentioned the news. So is this something, are the problems with talking about neurology, is it the way that the media is presenting it, or is it something about the field itself?
Part of the problem is with the media. Part of the problem was with the unbelievable seductiveness of being a public figure for the neuroscientists themselves. And I wouldn't hold myself out as above them. I mean, it's very hard not to be seduced by the fact that everybody wants your opinion all of a sudden when you've gone from sort of a backwater specialty in terms of a low visibility to one which is the sort of the pinnacle of public view at present. So I think part of it is there's an attempt to clarify and simplify complex issues for the public on the part of the scientists, part of the journalists. And there's no such thing as a maybe journal, and there's no journal of negative results. So basically, you have to frame things in a positive light in order to be heard above the din. So I think it's a little bit of everybody, and that would include myself.
Well, and this is also a particularly difficult area for the layperson to wade through, is it not?
You know, I've spent 12 years on these last 2 books, and even now, after I've written them, if I go away from it for a few days and I go back and pick up something I've written, I go, is that right? And part of it actually stems from the way our minds work. In other words, in the book I mentioned that we only have a small amount of memory. We can remember 7 to 9 digits, for example. You can remember maybe 4 chunks of information. And beyond that, you can't keep it in your mind all at once. So if you take a complicated idea, that, let's say, A leads to B and B leads to C and C leads to F and F leads back to D and so on, like, multiple interacting and perhaps self-canceling parts, it is impossible to keep in your mind all at once. So every one of these neuroscience questions has a number of possible interpretations, and some of them arise from yet other kinds of studies that have myriad interpretations. For example, if you take a concept like free will or consciousness, they're not simple ideas. So it's impossible to keep them in your mind all at once. Once you put them in your subconscious, they're subject to all the biases, they're subject to forgetting this or that, and it's enormously difficult for the public, let alone for people like me, to keep them all in mind. As a result, clarity requires oversimplification. Oversimplification almost invariably leads to reductionism, which is probably where we exist today in the field of neuroscience.
Is that why we're seeing so many cross disciplines? Things like neuropsychology or neuroeconomics or cognitive neuroscience. Is that part of the issue?
It's the old Willie Sutton joke. If you want to rob somebody and get money, where do you go? Well, you go to the bank because that's where the money is. Well, the money's in neuroscience now. If you're a philosopher, you're more likely to get funded if you have an fMRI scan to substantiate your study on, let's say, on free will, than if you're just having an armchair idea. So you see philosophy, you see behavioral economics, where anybody who's been through a couple stock market crashes realizes that old economic theories are not 100%, on the money, as they say. So if you can augment it with an fMRI study or something that will capture people's attention, all the better. And I'm sure you're aware of the studies that have been shown. If you take the same logic with and without an fMRI study on something that's incorrect, it will turn out a greater percentage of people will think that the study is correct if it has an fMRI cited. Well, so if this is the case, it's no wonder that everywhere you go, it's fMRI to the rescue of fields that otherwise might, like social psychology, for example, that might otherwise go into the backwater. And I don't say this to be critical, because each of them has their own place, but they're at different levels of understanding of how we human beings tick. But unfortunately, the proof is in the image in terms of the general public. So I think a lot of these fields are the expected outcome of advance of technology.
This is Skeptically Speaking, and I'm joined by Robert Burton, neurologist and author of A Skeptic's Guide to the Mind, What Neuroscience Can and Cannot Tell Us About Ourselves. Okay, well, let's hop right into some of the biggest questions, and we'll talk about some of the obstacles along the way. So what can neuroscience tell us about what we think of as ourselves? The idea sort of where we end and not we or the other begins. Where does that come from?
The study of the brain, which is, strictly speaking, basic neuroscience, is science. The study of who we are is a combination of literature, philosophy, drama, the arts. It's everything. It's a composite and a potpourri of a variety of different ways of looking at things. Studies of the brain can give us great insights into who we are at the level of thinking about basic processes. So let's just take the idea of, you mentioned the self. For years, there's been this old mythology that you can have out-of-body experiences, as an example of being visited by people from other planets or channeling of muses or whatever. But more recently, we have found that you can stimulate an area of the brain, the right temporal parietal junction, and create out-of-body experiences in perfectly normal people at will. You can also create this with certain chemicals. And so now it's clear that you have out-of-body experiences on a physiologic basis as opposed to any otherworldly kind of explanation. As a result of studies like this, you begin to realize that the brain creates what they call representational maps. Those are neural circuits that contain a set of interrelationships that collectively create a function. For example, if you want to learn to play the piano, you first learn the notes on the keyboard, you learn where your fingers go, you learn the sound of the music, etc. All of these collectively would make a representational map for piano playing. Well, it turns out that the brain makes representational maps for lots of things, and one of them is the physical sense of a sense of self. So the sense of self is actually a collection of involuntary mental sensations that the brain uses to tell you about what it's doing, and it needs to have a sense that you can imagine yourself in time and space. In other words, if you want to plan for the future, you have to have a physically embodied presence that can move through space. Otherwise, you couldn't think about the past and you couldn't plan the future. So for evolutionary reasons, we seem to have evolved this sense of a personhood. And that's, so they refer to that in the literature as a phenomenal, and I don't mean by that as wonderful, but phenomenal as in the phenomenology of a sense of self. And so that's where we begin. We begin with these neural networks that collectively interact, and there we are.
So can you tell me about some of the research that's been done in this area? Because, as you said, the root is not just neurological, it's psychological and physiological as well.
Well, so for example, there are myriad different kinds of studies. For example, it turns out that people with delusions of being possessed by others, people with schizophrenia, are able to tickle themselves. Now, you wonder, how is that possible? We aren't able to tickle ourselves. And it turns out that we operate in large part as predictive devices. For example, if you're trying to catch a Frisbee, you have to sort of predict where the Frisbee is going to be, and then you run towards it. If you're going to play a musical instrument, you sort of have to predict what your fingers are going to be doing in the very near future. So our brains are very good predictive devices. And when things are going smoothly, they don't tell you all the very details about this. What they really tell you is that things are fine and you don't need to be bothered with the details. But if something's gone wrong, such as in the disease of schizophrenia, you are suddenly left with no feeling of agency, so you fill it in. And the person who's done the work on this is a fellow named Chris Frith, Frith, University College London, and he's got an entire book out on the illusions of selfhood, that including the one I just mentioned, and it's well worth reading.
I do get confused when we're talking about these subjects sometimes because it seems like neurology really uses the language of psychology.
There isn't any other language to use. In other words, if I told you that there's increased firing in the cingulate gyrus and the left hippocampus has intermittent spiking, it doesn't mean anything. It is not translatable into any kind of behavior. The real problem is that pure neuroscience isn't quarks and mesons and gluons, it's behavior. We look at basic brain mechanisms and we have to translate them into the jargon of behavior, which by very definition is going to be folk psychology. He did this because he feels badly, he's humiliated, he's embarrassed. Well, to say that his pain matrix is lighting up is quite different than saying he stubbed his toe. There are different levels upon which we explain things. And so neuroscience, by the way it's been constructed, is really a science, but the explanation of human behavior has to still go back into folk psychology. Unfortunately, as you're probably aware from the controversy they've had about the DSM-5 versus the National Institutes of Mental Health in America.
Absolutely.
The behavioral descriptions don't map well onto the scientific descriptions. And so there's a huge dispute as to what do you do if you find that you have a genetic abnormality. What does that mean in terms of behavior? Or conversely, what if you have a behavior? What does it mean in terms of looking for what might be wrong? And so that there are two different levels of thinking about it. Both have their advantages and disadvantages.
Is there any inherent disadvantage to the fact that they use the same language?
Well, one of the problems, obviously, is the overlap in training. And let me just use one example that I have in the book about determining consciousness. The case in point, which has become a sort of rallying cry for neuroscience over psychology, is the woman who was 25 years old, was in an automobile accident and ended up in a vegetative state. In other words, her eyes were open or closed, but she wouldn't look around. She recognized nobody, was unable to respond voluntarily to a request, motor movements, etc. And she was in this for at least a half a year. And then they did a very clever study. It was actually done by a neuroscientist who's now is in Ontario, to try and compare this woman's brain with the brain of a normal volunteer. So what they did is they took a dozen volunteers and they asked them to first imagine walking around their house, and then secondly to imagine playing tennis. And then they saw certain areas on the fMRI scan that lit up. So they had certain normal patterns for people who were totally conscious. And then they put the headphones on this woman who was essentially unresponsive, put her inside an fMRI scan and asked her to do the same thing. And she had been a good tennis player before, so she knew tennis quite well. And lo and behold, her fMRI showed the same findings. Her same areas lit up in her that lit up in normal volunteers. So the conclusion from the neuroscientist was that she was conscious, fully alert, and aware of her surroundings and her condition. Now this is where the language of psychology comes in: conscious, fully alert, aware, and aware of her condition and surroundings. Okay, that was based upon the interpretation from the fMRI scan. But the problem is, if we go back to the comment I made earlier about these so-called representational maps, you walk around your house when you move into a new house. You walk around it enough times that eventually you're able to almost navigate in the dark. So you have a very well-constructed representational map of your house inside your head. The same thing goes if you play tennis. You learn how to do this gradually, and you develop a representational map for hitting forehand, backhand, etc. So all these maps are in place. So the real question is, what is the nature of conscious thought versus unconscious thought? In this woman, where she activated the same areas, it was included that she was conscious because this was a neuroscientist looking through his lens.
Right.
But if you look at it from the point of view of other studies and of how the brain works, and also from philosophic studies and psychological studies, we realize that we, as individuals, do most of our behavior unconsciously. For example, if you're at a cocktail party, you could be minding your own business and suddenly someone mentions your name and you suddenly turn around and you hear the name. Well, you weren't listening to the name. The name came in to your auditory cortex exactly the same way as these instructions came to this woman's auditory cortex. And your brain processed this unconsciously, and it felt, oh, they mentioned your name, you should be aware of that, and suddenly you became conscious of it. But the area for your name would light up. It's the same way if you said walk around your house and those areas lit up, your unconscious brain might create the same activity. Now, we really don't know. So the problem really is, how do we know whether this woman intended? And intended is a psychological term. It means that she wanted to do this. She was doing it volitionally, intentionally. Those are terms out of psychology. We don't know. We can't paste those onto the neuroscience thing. So the reality is she might be conscious, and she may well not be conscious. But it gets down to the definitions of conscious. So for me, it depends on whether or not neuroscientists have a strong working knowledge of psychology and philosophy at the same time as philosophy and psychology by themselves can't answer these questions except from a behavioral standpoint. If you're a psychologist at the bedside or a neurologist, you'd say she's unresponsive. If you're a neuroscientist at the bedside and you do this study, you say she's conscious, as they did. They made a proclamation that she was fully conscious and alert. The truth of the matter is neither answer is correct, and it's not knowable because you have different levels of looking at it. So you ask me, is there harm? Well, as a result of this study, hundreds of thousands of people with families in similar conditions are put in the awful position of, on the one hand, being told by their doctors correctly that there's little chance for their loved one to recover, and on the other hand, having a study which contradicts that, for which we have no evidence that it's actually true. So according to our old rules, she appears not to be responsive. According to our studies that have been done through the years in rehabilitation of people in coma, the odds of her making a useful recovery are quite limited. On the other hand, we now have a new piece of information that's confusing. It may alter different alternatives, but isn't yet an answer. So to me, when you say this is dangerous, well, I can't think of anything worse than being in a position of using imprecise language and incomplete data to affect a family in that way.
You're listening to Skeptically Speaking, and I'll be back to talk more with Robert Burton, author of A Skeptic's Guide to the Mind, What Neuroscience Can and Cannot Tell Us About Ourselves, after this.
Skeptically Speaking is rebroadcast on a number of fine radio stations. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm Desiree Schell, here with neurologist Robert Burton, author of On Being Certain, Believing You're Right Even When You're Not, and the new book, A Skeptic's Guide to the Mind, What Neuroscience Can and Cannot Tell Us About Ourselves. Okay, on to other big issues. What about our ability to make rational decisions? What can neurology actually tell us about that?
Imagine that conscious thought, as I mentioned earlier, is a tip of a cognitive iceberg. And by that I mean, if you can only have a few items in memory at one time, and if you were to talk about climate change, and let's say you have 4 items in memory, and then somebody comes up and mentions 4 more items that he wants you to consider as part of climate change, the first 4 cannot stay in memory along with the other 4, so that you can now have 8 different items in memory. We just don't have the facility for that. So in order to consider the second 4 objects, questions about climate change, you then have to put the first 4 into long-term memory, which means that it's now sent down to the unconscious, into the cellar of your head, so to speak, where it is now subject to every bias that you have. It will be reshaped, reformed, and anybody who keeps up on modern psychology realizes that memory morphs over time. That, let's say, if I'm thinking about climate change and right while I'm doing it, suddenly it gets really hot where I am, my thoughts might change. If I hear a bluebird outside, I might change. But it might change at a subconscious level. Then when the memory comes back again, it has been morphed, changed, altered, in some way mutilated by its trip through the unconscious. So when you think about reason, for the last several hundred years, we've had this kind of concept of pure enlightenment, of pure rationality, pure reason. And even while I'm talking to you right now, I am using reason as a way of explanation. We can't get around the fact that we have a very strong sense of reason. But the truth of the matter is, what neuroscience has shown us is that we have lines of reasoning that we feel are correct, but we don't even know if that's how the brain constructs the thoughts in the first place. For example, we know that the brain operates primarily in parallel. For example, simultaneously it's doing hundreds of different odds and ends while we're talking right now. Those are all done in parallel, and it may be that when we have a complex thought, that it doesn't occur serially, meaning thought A leads to thought B, leads to thought C. Mm-hmm. And maybe it's all occurring at once, like as some people would say, like getting the bigger picture, getting a gestalt. Or it may not even be that lines of reasoning as we experience them consciously are the same as the way they're actually occurring in the brain. And on being certain, I use the example of the baseball being thrown to the batter. In reality, as soon as the ball leaves the pitcher's hand, the batter has to start to swing. It takes him like 200 millisecond reaction time to even get the bat off his shoulders, and then it takes another approximately 200 milliseconds for him to swing the bat across the plate, which is about the same length of time it takes a ball to go from the pitcher's hand to the plate. So what happens is the ball leaves the pitcher's hand, and within a very, very short period of time, the batter has to decide what to do, and then he starts to swing. But what he sees from a perspective of the description that he will tell people later, is he sees the ball approaching the plate, and then he decides to swing. But that's not the way it could have happened. They couldn't have seen the ball approach the plate and then start to swing. But it would make no sense for them to swing when the ball is just leaving the batter's hand from a visceral standpoint. So what it amounts to is, it turns out the brain has a way of reconstructing time. It's called subjective backward representation of time. So it projects the image in such a way that we see it in a way that's consistent with how we behave. And this is true for all high-speed sports. Almost every high-speed sport, people start to swing immediately. But then they say they saw the punch approaching the head and then they ducked. So the description isn't consistent with what actually happens physiologically. If that's true, then you can understand that we might have a sense of the thought A caused thought B caused thought C occurring sequentially. But in fact, it may not have anything to do with how the brain actually works at a physiologic level. They may be having hundreds of inputs all in an instant. It gives you a new idea, and it seems to you that is a logical follow on from what came before. And this gets back to what I mentioned earlier about these involuntary mental sensations and the whole feeling of causation, which goes all the way back to David Hume in the 1730s, but basically saying that we are but a bundle of sensations. My book is really just a neuroscience update of what he said almost 300 years ago.
This is Skeptically Speaking, and I'm talking to Robert Burton, neurologist and author of A Skeptic's Guide to the Mind, What Neuroscience Can and Cannot Tell Us About Ourselves. Can I just read this one quote from the book that I very much enjoyed? You said, "Hiring the mind as a consultant for understanding the mind feels like the metaphoric equivalent of asking a known con man for his self-appraisal and letter of reference."
I can't add to that.
Okay, so let's talk about this then, because I feel like we've bashed neuroscience for quite a while. So how can we even begin to study the root of rational thought or morality or consciousness or whatever we're trying to look at if our brains are so spectacularly unreliable? Can we ever really trust our study design or our interpretation of the data?
First, you have to divide questions into those for which it's conceivable there's an empirical, scientific methodology accessible answer. For example, if you ask me what the speed of light is, that's pretty simple. You can figure it out somehow. When you get beyond pure science to language, you have a huge impediment, which I've already discussed, but basically extrapolating the firing of a cell in the prefrontal cortex into making observations about mirror neurons or empathy or the roots of morality, that's not a scientific statement anymore. That is a statement of opinion, of subjectivity, of it's a story that is being woven by the scientist about the implication or the long-term downstream value of his studies. Now, it's impossible to get away from those because you wouldn't do these studies unless you didn't believe they had this long-term downstream value. On the other hand, there's no evidence that we can ever discuss morality scientifically. It's not an evidence-based concept. Again, I want to emphasize that science is the only way of knowing the real world insofar as having a scientific methodology. But that won't get us to bridge the gap to subjective phenomena such as the nature of our conscious experience and behavior and so on.
Maybe let's look at it from the other direction then. What kinds of questions can neurology answer?
Let us say that I do an fMRI scan on people that have committed murder. And I find that in a certain number of people who with recurrent bouts of violence, that they show a defect in the prefrontal area, okay? And we do more advanced studies, and eventually find out that there's certain circuitry in the brain that is defective. That can help you understand the nature of violence. Now, that becomes additional data upon which you can make subjective judgments about the degree of responsibility the patient has towards its crimes and so on. In other words, it gives you more information, and over time we'll have to learn how to assimilate that into a sort of popular common consensus of what it means. But that consensus isn't going to rise out of the science. But without that information, you really operate in the dark ages. So it's a great advance to know that people with recurrent attacks of violence have a higher propensity towards these defects. It helps you judge them in a more humane, scientifically consistent way, but it isn't the final answer.
So how about those, when we see news stories that say neurology can tell us everything from whether we'll be good parents to how we vote? What are your thoughts about that?
My thoughts are that's why I canceled the newspaper. I have gotten tired of reading this. I get a newsletter. I get something every day that makes my blood pressure go up. But in between all these things that make my blood pressure go up, there's some utterly fantastic advances. But they're not usually at the level that are going to be headlines. Unfortunately, it's partly the problem of way sound bites, media, attention span. It's really hard. This took me 12 years to write these two books and probably 30 or 40 thinking about it. And it's been an obsession of mine. And even at this juncture, I don't have good answers. I mean, if I wanted to write the world's bestseller, I would give you bullet point answers for how to do these things. It's really difficult. But really difficult doesn't sell. Really difficult doesn't get on the news.
Well, I was going to say the short form of your book would just say, in all caps, it's complicated.
One of the studies I was going to mention, a rationality, was the Kruger-Dunning study, in which they took people that were going to go to Cornell, and then they administered a number of tests, and one of the tests was on logic, and it turned out that the people who did the worst on the logic test, the people who got down to the bottom 12%, estimated that they were at the top third. They did worse at self-estimation than those that did better. And that when they were presented with the opportunity to change their minds, when they saw how the other people did, they did not change their minds. So the conclusion was they had a dual defect. A, they couldn't tell that they did poorly in terms of logic and testing for logic, but were sufficiently illogical they couldn't tell if they were doing poorly. But these were not like idiots. These were people that got into Ivy League college, and they were obviously smart people. And what it's done is it's taught me a little humility in dealing with others, is really that what neuroscience has taught me is that we're all victims of an enormous number of irrational and largely undetected and biases from which we simply can't get beyond. I think in that sense, what neuroscience might be helpful, in addition to all the things it's teaching us about science, is if we actually accepted some of these findings, we might be more tolerant of other people's differences, even if we disagree with them. I mean, the science versus religion controversy, which eats up so much of people's times, really comes out of fundamentally different ways of feeling about the universe, over which we have very little, if any, control. There's some people who are absolutely certain of their belief in God and so on, and they've had born-again experiences, epiphanies, and so on. And there are other people who've had epiphanies that they're atheists. Well, in Identical Twins Raised Apart, they did a bunch of studies on personality traits, and it turns out that certain traits seem to supervene culture. So the Identical Twins Raised Apart, if one guy has religious tendencies, the correlation is almost perfect for the other identical twin, even though they never had contact with each other, having the same degree of religiosity, as they called it. If one person's interested in religion, then his identical twin is quite likely to also be interested in religion of some sort, whether it be, one might be Jewish, one might be Buddhist, one might be Islam, whatever. And you know, one of the people that is a strident atheist nowadays that you know personally was formerly a born-again.
Right.
And what's really fascinating to me is that there's a very strong urge towards absolutism. There's an urge for that feeling of knowing. And other people, like myself, have very little sense of feeling of knowing. Even like I mentioned earlier, when I've written this book and I spent 5 years on it, and then I pick it up after, when I go to give a talk and I read something, I go, is that right? You know, when I talk to my friends and they tell me something might be wrong about it, I say, no kidding, that's interesting, you know. What I've learned is that this science versus religion comes out of these involuntary mental sensations that create much of what we think of as a mind. And if people would actually just see that that's the way it is, a lot of these arguments would just fall by the wayside. You just say, okay, he's different than I am. But somehow we think we can convince left-wingers and right-wingers and climate deniers, and we think we're going to convince them with reason. You're not going to convince them at all with reason.
At points in your book, and right now, you sound far more like a philosopher than you do a neurologist. Robert, thanks so much for being here.
Yes, my pleasure.
You'll find a link to Robert Burton and his book, A Skeptic's Guide to the Mind, What Neuroscience Can and Cannot Tell Us About Ourselves, on our website at skepticallyspeaking.com. And we'll be back with more Skeptically Speaking after this.
On the next episode of Skeptically Speaking, we're exploring the everyday experiments that take place in our very own kitchens. Desiree Schell speaks to Guy Crosby, science editor for America's Test Kitchen, about his book, The Science of Good Cooking. And geneticist and science writer Tora Kachur returns to the show to take a scientifically informed look at the future of food. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
This is Skeptically Speaking, and I'm Desiree Schell. I'm here now with Dr. Jeffrey Anderson, attending neuroradiologist at the University of Utah. Jeff directs the Functional Brain Mapping Service and studies the brain circuitry of neurodevelopmental disorders such as autism and Down syndrome. He's also the author of 3 internationally best-selling science thrillers and a finalist for the International Thriller Award, as well as the author of a forthcoming textbook on functional brain anatomy. Welcome to the show, Jeff.
Thank you so much. I'm so grateful to be here.
So you have done some research that's built around the idea that different sides of the brain control different personality traits. The left brain controls the analytical processes and the right brain controls creativity. And we've all heard that before. So where did we come up with the idea for that in the first place?
I don't know exactly how that arose, but it's based in some really good science. For example, around 30 years ago, there was work by people like Roger Sperry and Michael Gazzaniga who studied split brain patients. And we learned that the left and the right sides of the brain really do have some different functions. And I guess popular psychology enthusiasts kind of let their imaginations run wild with the idea.
That has never happened before.
No, indeed.
But this is something that many people have just taken for granted. Was that the public that put stock in that idea, or were scientists working under the assumption as well?
It has never been accepted in the neuroscience community that left brain or right brain dominance is really a valid basis for personality type. And there's some really good reasons for that. For example, we don't have those kind of personality shifts when somebody gets a stroke or a lesion to one side of their brain. And it would be a really inefficient use of brain energy to have one hemisphere consistently underutilized. But nevertheless, for whatever reason, that's just become almost unquestioned in many lay communities that there's actually some truth to that. And I don't think as a neuroscience community we've been aggressive enough in challenging that.
And that's where we come to your research. So tell us about it.
What we were looking at was brain networks. In particular, we were studying brain networks between regions that tended to be lateralized to one side or the other. And by lateralized, I mean that the connections are stronger or more active on one side of the brain than on the other. We've known that there are some areas or functions that take place preferentially on one side. For example, language is primarily a left-sided brain function in 95% of individuals, and attention to the outside world is mostly processed in the right hemisphere. So what we wanted to look at was, is there a grain of truth in this stereotype? Is it true that a left-sided brain network tends to be more active in some individuals than in others? And the way that we studied that was with a technique called functional connectivity. And what that looks at is studying the noise in brain images. It's relatively new, and you could think of it, I guess, as a third generation of brain imaging. So a first generation would be structural brain imaging, where you just take pictures of the brain. And then a second generation might be functional imaging, where you take pictures of blood flow that tell you what parts of the brain are active when someone is doing something. And then another technique entirely is to look at 2 parts of the brain and ask, are they synchronized over time? And when they're synchronized, they tend to be functionally related or connected. So it allows us to make a wiring diagram or a map of connections in the brain.
And so what exactly were you looking for?
What we were looking for were biomarkers. We study autism and Down syndrome and neurodevelopmental disorders. And it is also the case that the normal lateralization or dominance of some functions in one side of the brain or the other is different or abnormal in some way in many conditions like autism or schizophrenia, Down syndrome. It seems to be fairly prevalent that in many of these conditions, lateralization is abnormal. So we were hoping to exploit that to find a test that could look at these conditions by MRI.
And what were your conclusions?
Well, what we found, first of all, is that there are 2 broad networks, a network of regions that seems to just talk to each other in the left hemisphere, and another entirely separable network that seems to just talk to itself in the right hemisphere. And we were surprised how cleanly that fell out of the data. As soon as we started mapping out these regions of which ones were preferentially in the left dominant network and which ones were in the right dominant network, it occurred to us, well, we should take advantage of these really big data sets that are now available through data sharing and look at how individuals vary in the population just normally. Is it true that one of these networks tends to be stronger than the other one? And we really didn't know if that was true. That was the sort of thing that was hard to formally study before some of the newer techniques that have evolved in the last few years.
So the imaging was taken while the participants were resting, correct?
That's right. Yeah. So what we're actually doing is we image the brain about every 2 seconds. We image it over and over and over for, anywhere from 5 minutes to 20 minutes or more. And the idea is that for this type of imaging, subjects don't actually have to participate in any particular cognitive task. And that's different from what people are used to thinking of fMRI.
Right.
Because in this case, we're not measuring which part of the brain is active when you do something. You can even have just random noise or a spontaneous firing of a region that may not be associated with any particular function or task. And when that happens, then regions that are connected to that part of the brain will also have inputs and will have a higher chance of firing. And so what you get over time is that regions that are related are synchronized. And so it allows us to measure whether something is connected or not. And again, it constructs a wiring diagram. We can look at the strength of connections. We can look at how related any two regions are. So it really doesn't have much to do with what the individual is thinking or doing.
Well, would it make a difference to your conclusions if the participants were involved in some kind of activity?
It does modulate the results when you're doing a task, but the underlying network structure is pretty much invariant. So although it changes the strength a little bit in some networks versus others, the network architecture really doesn't change. And we've looked at that. We've looked at tasks as well. It's certainly a possibility, although I'm doubtful that you would see differences on that kind of scale to the conclusions.
So is there any controversy around your work at all? Do other scientists agree with your findings?
Coincidentally, there was another study published the same week by Stephen Gotts and some colleagues from NIMH. And they found some interesting findings that dovetail really nicely. They studied a smaller sample, but more highly controlled, and they also had some behavioral measures on these individuals. And what they found is that, for example, people who had the left side of the brain just in the language regions, very specifically to those regions, where it was more left lateralized in one person, that they actually tended to do a little bit better in language function, for example, higher vocabulary. That effect didn't generalize to the whole hemisphere, just as we found that it seems to be connection by connection or subnetwork by subnetwork where lateralization happens. So one individual might have some strong connections on one side and some other strong connections on the other side, but it doesn't tend to separate left-right, a whole network at a time. In general, in the scientific community, I don't think anybody was losing sleep over the idea that personality types were determined by left or right brain dominance. But I also think that it's one of those things that when you don't have an immediate answer as to why, it could certainly have been the case that the left or the right brain network as a unit could tend to be stronger in some individuals or others. And so I don't think that had been formally tested before.
So then on a practical level, what does this mean, since no one was losing sleep at all? I guess you've almost single-handedly taken down the personality tests built around
I think there have been people who beat their head against that wall long before me. But it's become so widely accepted in our culture that left brain and right brain dominance are valid concepts that, there are apps you can download to strengthen one side of your brain. It creeps into textbooks on learning styles in psychology. There's team building exercises at workshops that people pay money for to balance their brain or strengthen one side or find which side you are. Although none of these have really been proposed by the neuroscience community, it's remarkable in some ways how insulated neuroscientists are, and many scientists, from society at large. We have a very specialized field of study, and often we don't engage the larger lay community about questions like this. And in some ways, that's a little bit frightening because neuroscience affects so directly many of the moral and cultural values that we have in society. In fact, there was an editorial in one of the first issues of Nature Neuroscience, and the editors were commenting on how neuroscientists deal with very unsettling questions about the soul, about what it means to have free will, about what the source of moral agency is. And their comment in the editorial, which I thought was particularly insightful, is that if neuroscientists don't address these questions, then others will do so on their behalf, maybe with less data and with less information. And so I think it's a worthwhile thing to bring to public consciousness when we have the opportunity.
Since I have you here, I have to ask about your books. Science thrillers. Do tell.
I had a lot of nights on call at the VA while I was in medical school. And, you know, a lot of times, you know, you get called every 20 or 30 minutes to ask if, you know, get somebody some more Tylenol or something like that. And, you know, it's pretty insufferably boring. So I took to reading, and as I was reading science thrillers like, you know, some of the classics in the field by Michael Crichton and others, I thought, you know, it would really be nice to try a crack at doing one where the science was more accurate. And so I just couldn't help myself to start jotting down ideas, and ended up writing 2 books and then one more with a partner. I've kind of drifted from that now. I've been so excited about, you know, just doing the science that I haven't found time. It's a challenging market to write for. People are definitely very critical. And appropriately so. And so to try and throw your hat in that ring is intimidating. It's a lot to try and get all the moving parts working right, but it's fun.
At least you don't get emails when you mispronounce words.
That's right, just misspelled.
Jeff, thanks very much for being here.
Oh, it's my pleasure.
You can find a link to Jeffrey Anderson and his work on our website at skepticallyspeaking.com. My last guest today is Gary Marcus, cognitive scientist at NYU, who's published numerous articles on language, evolution, computation, and cognitive development. He's the author of 4 books, including Cluj, The Algebraic Mind, and the New York Times bestseller Guitar Zero, and he's also the co-editor of the forthcoming book, The Future of the Brain, Essays by the World's Leading Neuroscientists. Gary frequently blogs on science and artificial intelligence for The New Yorker. Welcome to the show, Gary.
Thanks very much for having me.
Now, we've invited you on today to talk about a piece that you just wrote for The New Yorker called The Problem with the Neuroscience Backlash. But maybe before we get to the backlash, or rather to the problem with the backlash, there's actually a real issue that people are lashing back against. So maybe tell me a little bit about what you call pop neuroscience.
Well, I think probably for about the last 15 years, it's been possible to do brain scans of people doing basically anything, whether they're playing chess or having orgasm or whatever you might be interested in, and then you can show some color picture of, you know, this is your brain on X, this is your brain on music, this is your brain on drugs, etc., etc. Often the interpretations of these things are simplistic. It's very easy to say, look, these 3 things light up when the brain is doing such and such, and this explains how the brain is analyzing this. The problem with that is that many of the interpretations have been very naive. Sometimes people only do 1 or 2 experiments. They don't consider alternative hypotheses. And often in reality, many different circuits in the brain are contributing to some behavior. And so it's often naive to simply say this thing lives in this spot. So emotion is in the amygdala, for example. So it's true that a lot of the things that contribute to emotion are in the amygdala, but the prefrontal cortex plays a role in emotion as well. And generally, when you track down what's really going on, you're going to see lots of different contributions to how the brain works. So in the last few years, people have started to realize this. They've started to realize that the original studies are in many ways naive, and I think there's a lot of well-placed criticism. I think the new book by Sattel and Lilienfeld does a really good job of laying out some of the worst inferences that have been made. So there's some bad neuroscience out there. There's no question about it. And I think people got too excited too quickly about these brain imaging studies. Part of the problem is that these studies are looking at too coarse a level. So it's almost like looking out at an airplane window and trying to figure out what's going on the ground. The level of resolution in a brain scan is such that an individual voxel, which is the equivalent of a pixel, three-dimensional pixel, has somewhere between 100,000 and maybe even 1 million neurons inside of it. And the real action of the brain is at the level of individual neurons and how they interact. And so when you're looking at a cluster of 100,000 neurons, you don't really know what's going on in detail.
It almost seems like we as a people have gotten sort of unreasonably obsessed with neuroscience as well.
Well, and I think the critics are right to point out that the prefix neuro has gotten attached to everything, and it becomes this kind of prestige word that doesn't really mean that much. So you've got like neuro law, and neuroeconomics, and neuro this, and neuro marketing, and so forth. And often the neuro part isn't really telling us that much that we don't already know. I think it is possible in principle that it will, but at least for now, what most typically happens is psychologists have worked out some theory over 30 or 40 years. Somebody goes in, they do a brain imaging study, and it's consistent with that original hypothesis that's come out of psychology. But when it comes from psychology, it's sort of not that prestigious. It's just something you learned in your intro psych class. When you see a color picture in the brain, you get very excited. Aha, so there is a place in the brain that represents value, for example. Well, of course there's a place in the brain that represents value. We wouldn't be the kind of creatures that we were if there wasn't. But some people say, aha, because I can see this, sometimes we crudely call it these spots on the brain, now we understand everything. The truth is we don't. The spots are kind of like a guide to the geography of the brain without telling us the details of how those circuits work. So it'd be like saying, aha, the way the United States works is that politics is in Washington, D.C. Well, that would only be sort of right. I mean, a lot of politics does go on in Washington, D.C., but that wouldn't tell you how Congress works. It wouldn't tell you how lobbying works. It wouldn't tell you that people can lobby from New York. They can lobby from California. So it would be a vast oversimplification to say politics lives in D.C. It might be the most dominant place where politics happens, but it's certainly not the only one. And it would be really reductionistic to attribute politics just to D.C. And in the same way, when you say emotion lives in the amygdala, you're ignoring the contributions of many other parts of the brain, most notably the prefrontal cortex. But vision can contribute to emotion, for example, and just about anything in the brain can in some way influence emotion. So it's way too crude to just say, this is the thing that matters.
So then getting to the backlash, the book Brainwashed is not the only example of that. Scientists do seem to be pushing back now.
Well, I think different scientists go in different ways. You're definitely right that that's not the only book. I think it's the one that's done the best job of sort of laying out all the things that can go wrong. I think that within science, there's really different scientists doing different things. So there are some that are sort of sticking to the neuroimaging exactly the way that it's been done for the last 15 years, and other people that are trying to do better things. So if I have a fault with that book, it's that it's not looking at the cutting edge. It's kind of looking in the rearview mirror. It's explaining what did go wrong in the preceding 15 years without saying, well, what can we do next? And there are people doing interesting things that they mention only briefly and don't, I think, allow enough for. So one example is that there are some people in Berkeley, led by Jack Gallant, who have looked at this question of, well, maybe there are many different contributions to the brain. Does that mean we can't understand it at all? I think actually the worst offender here was David Brooks had this New York Times piece, which I critique, where he kind of seemed to suggest if something doesn't happen in one particular place in the brain, we should just throw up our hands. And I think that's a silly conclusion. Just because something isn't in one spot doesn't mean that we can't understand it. The circulatory system, for example, is something that's spread throughout the body. I mean, sure, the heart is kind of the focal point of the circulatory system, but you've got veins and arteries and so forth spread throughout the body. And we can understand that system as a whole, even though it's not localized in one spot the way, say, the liver is. I mean, the liver is one physical spot, but the circulatory system is spread throughout the body. And it's going to be the same thing in the brain, that rather than finding a particular cognitive function in a single spot, we're going to find that many cognitive functions are spread throughout the brain. And what we want to do is to understand how those parts work together. So back to the study I was alluding to by Jack Gallant, what he did is he showed people movies recorded from essentially the entire brain and then tried to guess which part of the movies they were seeing based on those images. And he threw some pretty fancy mathematics at the problem. And he discovered he could do pretty well. If you go to his website, you will see that he can do a fair job of reconstructing what you're watching in a movie just by looking at your whole brain and making guesses about what other patterns of neural activity are most similar to this particular one. So the backlash is saying, we haven't done a very good job of neuroscience. And what it really means is we haven't done a very good job with neuroimaging. There's lots of neuroscience that's great that people aren't talking about at all. So people studying individual neurons and how individual neurons start to fit together in circuits. There's a lot we don't know about, say, what happens with 10 or 20 or 100 neurons working at the same time. That's what we really want to know. But there's lots of people that are working on that in really interesting ways. So I think the future of neuroscience is pretty bright, and the people in the backlash aren't really distinguishing between problems with neuroimaging versus the likelihood that neuroscience, as a larger field with a lot more tools that are developing very quickly, is going to tell us a lot.
Well, and that seems to be the major issue right now is we have the two positions that are completely opposed. We have people giving far too much credit to neuroscience, and then we have people like David Brooks who seems to want to just abandon neuroscience and brain imaging altogether. So I guess I'm curious, which one is more dangerous?
They're probably both dangerous. I mean, I think we really do need to steer a medium course here. So the first thing we need to recognize is our behavior, our minds really are a product of our brains. I mean, Brooks came pretty close to arguing for dualism, saying we don't really need to know about the brain in order to understand ourselves, or knowing about the brain isn't going to tell us much that's useful. And I think that that's silly. I mean, it's obvious that the brain is critical to our behavior. It's obvious that we can mediate our behavior with pharmaceuticals, for example. The brain lesions change our behavior. There's no question about that. But at the same time, I don't think that neuroscience should be like the prestige science that dominates all others. So I think neuroscience is really important, but psychology is really important too, for example. Economics is really important. So neuroeconomics is not going to get rid of the day jobs of economists. It's not going to answer all the questions of economics just because we can say what part of the brain calculates value and economic reward. We're not going to stop needing to do linguistics if we want to understand how the brain processes language. Even as we understand the brain parts that contribute to language, we're still going to need linguists that explain things at a different level of description. It's like just because we know physics doesn't mean we don't still need chemists. And I think the problem is that some people think that the lower level science, like the one that's closer to the atoms, is going to be the one that explains everything. Right. But that's not really true for chemistry and physics, and it's not really true for neuroscience and psychology. So there's a philosophical position that says we won't need psychology anymore once we understand neuroscience. And I don't think that's realistic anymore, that we don't need geology now that we have physics.
Well, see, this is great for people who are cognitive scientists or neuroscientists. But of course, I do have to ask, how is a non-scientist supposed to tell if a particular study or news story actually sort of hits the sweet spot in terms of moderation, or if it teeters off into one direction?
I don't think that's an easy question. I started writing for The New Yorker and keeping this blog because I think we need more scientists in there explaining these things. So I think that journalists aren't always trained in the fine points of experimental methodology and so forth. I think we're starting to grow a new breed of journalists that's actually better at this. But historically, I think journalism has pressed towards sort of sensationalizing a particular study and making it sound like more than it is. Now we have some great blogs like Neuroskeptic, for example, where people are more critical. I've tried to do this myself in The New Yorker. I think you do need to look for scientists for their take on particular things. I think if there's a question that you care about, you should read multiple studies, multiple articles, not assume that any one article is going to tell you the truth, because usually the most recent article is going to talk about the most recent finding, and it's not going to try to put it together for you. And so you want to find a journalist or a scientist who is looking at the big picture, who can help you interpret it. I don't think there's a magic solution there, but I think if a question's important to you, you've got to realize that the thing that's hot off the press is usually not well integrated with the whole history of the field, and you need to do more reading in order to put it together. That's probably true in any domain of journalism. So, you can read about what's happening in Syria this week, but if you really want a true picture of it, you need to go back further than what you're going to find in your daily newspaper.
Gary, thanks very much for being here.
My pleasure.
You'll find links to the work of Gary Marcus and all our guests on our website at skepticallyspeaking.com. While you're there, click the links to connect with us on Facebook, Twitter, and Google+, so that you can keep up with show news, and of course to iTunes, where you can subscribe and listen to past episodes. Thanks for listening, and we'll see you next week on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.